Let's imagine that I have equation x dot is minus alpha x. Plus alpha x, but alpha negative. Okay, so apply Euler scheme. Minus xn equal to delta t times value of the function at xn is alpha xn. So this gives us xn plus 1 is 1 plus alpha delta t xn. By the way, for alpha less than 0, I know the solution. In fact, I know the solution for all alpha. So it is x is e to the power alpha t x0. And for alpha negative, it goes to 0. Right? This function is decreasing in t. So my numerical solution should also be decreasing in t. And when will this function decrease in t? So xn plus 1 is xn. Okay, assume x to be positive. I can take a mod if you like, but let's assume x to be positive. Then I want this object to be less than 1. Right? Then I know that xn plus 1 is less than xn. Ideally, you should say mod. Okay? So mod of xn plus 1 is less than 1. I want that be less than 1. Alpha is negative, please remember, alpha is negative. So it's great if delta t is small and alpha is negative, then this object will be always less than 1, no? Because this 1 minus, right, some positive numbers. But if imagine that delta t is, let's say, minus 3 alpha by delta t. No, sorry, 3 by delta t. What I'm saying, 3 by alpha. Just imagine that I choose delta t is minus 3 by alpha. Then what happens? Then xn plus 1 will be 1 minus 3, right? So it's minus 2 xn. And what happens for this situation? Will xn plus 1 decrease with time or no? Is minus 2. So if we start with, let's say, 0.1, so this guy will be minus 0.2. Then after that, again multiply these things with 0.4, then minus 0.8. So it's just increasing. Okay. So magnitude wise, in fact, it's oscillating. It's oscillating. And which is not what I want. I want the function to decrease with time. Okay. So this is definitely a problem. So if I choose delta t like this, problem. So I should not choose delta t like that. So that's issue. If I choose delta t large, then there is a difficulty. In fact, you can easily see here that if my 1 plus alpha delta t is less than 1, it is fine. If it is greater than 1, problem. Okay. Now I'm going to describe in a graphical way what this condition means. And this is true for all alphas. Alpha complex, this is a problem as well. Okay. So let's make a statement I'll make in the next slide. This is what I plotted it. Okay. So this equation for x dot is minus 100x. So the condition 1 plus alpha delta t less than 1 tells me that delta t must be less than, you can easily check that it's a 2 by alpha, 2 by mod alpha. Okay. So 2 by mod alpha is 0.02. Okay. So This one is fine because it's less than 0.02, and that is corresponds to the green curve. But this one is above 0.02, and that is oscillating. So this is a blue curve. This is oscillating. Okay. So if I use anything beyond 0.02, my solution will be not correct. Now, this problem also happens for complex alpha. So the simple example, if I have I pi, the example which I did, I pi was spiraling outward. So we have 1 plus alpha delta t. So alpha was minus I pi delta t. What is mod of this? Is it greater than 1 or less than 1? Is greater than 1, no? Because this is real and imaginary. In fact, this is square root 1 plus pi delta t squared. So this is greater than 1. So this one is for any delta t. There's, in fact, the problem. For any delta t, this is going to be exploding outward. If alpha is complex, then for real part of alpha less than 0, negative, no, so function is supposed to be decreasing to 0. But if I use Euler forward scheme, then I know that this mod will be greater than 1. We can verify it. It's greater than 1, and it just goes. It's not suitable. Okay, so complex alpha, there is a problem. Now, so we define what is stable method. Stable method is one which produces a bounded solution when the solution of the ODE is bounded. So exact solution, okay? So the exact solution is bounded, and what method produces a bounded solution, then is stable. And we want this scheme, okay? We want stable solution. But some schemes do not satisfy this property, and the method which is not stable is called unstable. Now, we can define it further. It's conditionally stable if it is stable for some parameter and unstable for some other parameter. So x dot is minus 100x is conditionally stable because for delta t less than 2 by mod alpha is stable, but beyond it is unstable. So this Euler forward scheme is conditionally stable for this equation. Unconditionally stable. So method is unconditionally stable if it is stable for all parameter values. Okay, I will show in the next class that Euler backward scheme is unconditionally stable for this equation. Any delta t will be stable. Okay, but that is a later class. Now, unconditionally unstable is if it is unstable for all delta t. Of course, Euler forward scheme is unconditionally stable for this equation. Okay, this is pure imaginary and it's unconditional. Any delta t I choose is going to explode. Okay, so the plot is following. So my alpha can be complex, no? So we have real alpha and imaginary alpha. But when real alpha is negative, so this part, now Euler forward scheme. So this is only Euler forward scheme, okay? Euler forward. So this region is stable. Okay, so you can verify that it is 1 plus alpha delta t less than 1 is a circle with center at minus 1. Okay, so within that is stable, and any delta t outside this region is unstable. Okay, of course this part is solution itself, it grows, no? For real alpha, a solution will grow. So both numerical as well as exact solutions grow. No problem. I cannot define stability on this. But stability is defined when exact solution is decreasing in time. But when numerical solution is oscillating or diverging. So this is the different definition than what we do in mechanics. In mechanics, definition is any small perturbation, does the solution take you away from the equilibrium position? But this one is very different. Okay. Now, so I think I'll skip this part. So the equations which we discussed today, so x dot is minus x, delta t less than 1 is stable, delta t greater than 1 is unstable. For I pi z is stable for no delta t. So this is unconditionally unstable. Unconditionally unstable. X dot is alpha x, it is same as that one, okay. But alpha is complex, so you have to put a mod. Actually, I should. Well, anyway, I assume real right now. Okay, so now this one is a bit tricky. This is a nonlinear equation. So nonlinear equation, there are ways to say about stability, but I'm running short of time, so I'm not able to describe. So the idea is that you make a linearization around given x and see whether linearized equation dA by dx is less than 0, like alpha is less than 0, and then you compute delta t. Okay. Now this argument is somewhat complex, but for all delta t, because of the nature of the solution, this stable. And this equation is nonlinear, but stability basically follows from here because I linearize it, so that's sorry, dA by dx. So this term determines the stability. And while so it's stable for delta less than 100, 1 by 100, and unstable for greater than 1 by 100. Okay. Okay. So nonlinear equation, if you want to do the stability analysis. So I want to perform the stability analysis as xn and tn. So this is, so I linearize around this. So Taylor series, okay. So this function of x and t, so I have to do two terms. So this and this. Okay. Now this can be written, this called x prime and this is t prime. Okay. So equation for from here, I want to make a change of variable. Okay. So in change of variable, x prime, so this dot near x and tn is this equation. And it turns out stability basically matters on this term. Okay. These terms, if they're well behaved, they won't affect the stability. Okay. So essentially, you look at this term, okay, which is partial f partial x. Okay. Now stability depends on this, so we want 1 plus alpha delta t, this alpha less than 1. Okay. So it's a somewhat, it's not a rigorous proof, but it's an intuitive statement you make that here alpha will be partial f partial x. Okay. Alpha is not a constant for all x, it varies with x, but you compute local alpha. So if I look at partial f partial x, what will I get? I get x minus 100, no? 2x minus 100, correct? This one. Now it turns out x is very small, x is tiny. This we see from the solution. So this is approximately minus 100. Okay, so that means it boils down to this equation. And that's why we get this condition. Okay, so it's a bit complicated argument, but that's the answer. Okay, so this is described slightly in more detail, not in much more detail, a book by Farzizer on numerical methods for engineering applications. Okay, he's a famous author, and so we can look at this book.